Hey everyone, Kevin here with another edition of Santa Rosa Junior College Wine Studies Online. Today we're going to review the NOPA assay. So what are we doing when we test when we use the NOPA assay to test nitrogen? We are interested in the total amount of nitrogen in a juice because that nitrogen feeds yeast and will ensure that we get through our fermentation successfully. So the total nitrogen that feeds yeast we refer to as the yeast assimilable nitrogen. So that's what yeast can assimilate. That's made up of two things. So YAN consists of two things together, the free amino nitrogen and the ammonia. The free amino nitrogen is the free amino group in an amino acid, as we talked about in class, and ammonia we talked about as well. Just remember that at wine pH, ammonia NH3 becomes the ammonium ion. It picks up a proton to become NH4+. So together, free amino nitrogen and ammonia make up yeast assimilable nitrogen. So free amino nitrogen, that's what we test by the NOPA assay, and that's what we're going to talk about today. Of course, the ammonia is tested by ammonia probe. Okay, so the NOPA assay can be done by just following a recipe. But I want everybody in the class to understand a little bit more about where we get the numbers. So the recipe is simple. You fill the cuvettes with just 3 reagents. Remember there was the buffer, then either the standard solution or the juice or water for a blank. And then you add the OPA solution and you get your absorbance at 335. So you can do that for the isoleucine standards and for the juice, and it's real simple. You get your A335, then you take your A335 and your nitrogen numbers, which you can just read off a table, and you can use those to set up your standard curve. Once you set up your standard curve, then you can get an equation for the standard curve in Excel, and then finally you use that equation in the standard curve, or the equation you got from Excel for the standard curve and the absorbance of the juice, and you can calculate the free amino nitrogen in the juice. So that's the basic process, right? So let's talk about how we get to some of the numbers. So it's good to know how we go from isoleucine to mgs of nitrogen. So isoleucine is our amino acid. It has that we use as a standard in the NOPA assay. It has a molecular weight of 131.17, and here's its formula: 6 carbons, 13 hydrogens, 1 nitrogen, and 2 oxygens. So I set up this little table over here with 6 carbons, 13 hydrogens, 1 nitrogen, and 2 oxygens. And here's the atomic weight of those elements. And if we just do the math, it means that in our molecule, isoleucine, we have 72 carbon, or 70 of the 131, 72 of that molecular weight comes from carbon, right? 12 is the atomic weight times 6. 13 from hydrogen, 13 from hydrogen, 14 from nitrogen, and 32 from oxygen. That makes up the 131. So in every molecule of isoleucine is 1 nitrogen, and in every 131 grams, right, that equals 1 mole. Right, mole is just a measure of quantity, right? It's 6 times 10 to the 23rd molecules, or 6 times 10 to the 23rd particles of any substance. In this case, it's 6 times 10 to the 23rd molecules of isoleucine. So in every mole, that would equal 131 grams of isoleucine, and in that contains, let's say it contains 14 grams of nitrogen. Okay, so then if we had 1 millimolar, let's say we had 1 millimolar of isoleucine, and isoleucine is abbreviated ILE. That's a 3-letter abbreviation for that particular amino acid. In 1 millimolar isoleucine, we would have, that equals 131 milligrams. Right, so it's 1 millimole per liter is 1 millimolar. So that's 1/1000th of a molar, right, millimolar. is 1/1000th of a molar. So that we would have 131 milligrams, or 1/1000th of a gram, right? Milligrams to grams, 1/1000th. 131 milligrams of isoleucine, and in that contains, sorry, my writing is bad on this little tablet, that contains 14 milligrams of nitrogen, right? So for every 1 millimolar concentration of isoleucine in our standard solution, we have 14 milligrams of nitrogen. So what do we do here when we set up the assay? We get to the next slide here. We set up the 4 standard solutions, the standard for doing the standard curve, the solutions like this. We had a certain quantity of isoleucine solution, and I mistakenly left out the units here. Should always put in the units. Those are milliliters, right? And that second row is also milliliters. So we had either 0, 10, 30, or 50 milliliters of the isoleucine solution. And then we made up the difference between that amount and 50 with water, right? So we always had 50 in our total in all 4 solutions. So let's take that second cuvette. Let's take the second cuvette and just talk about that one. And there we had 10 millimolar isoleucine and 10 mils of 10 millimolar isoleucine and 40 mils of water, making up 50 mils total. All right. So that is a 5 times solution, right? Because we had 4 parts water plus 1 part. All right, I can't even write at all today. 4 parts water plus 1 part of the isoleucine equals a 5x donation. There are 5 parts total, one of which is isoleucine. So we've diluted the isoleucine 5 times. So if we want to figure out the concentration of isoleucine in our 50 mils, so this is the concentration of isoleucine in 50 mils, in our 50 mil sample, that we would take the original concentration of 10 millimolar and multiply it by the amount of dilution, which would be 0.2, right, which would be 1 divided by 5. So we're really dividing it by 5, and that gives us 2 millimolar. All right, so we've got 2 millimolar solution of isoleucine in cuvette 2. Well, what do we know from the last slide? We know that for every 1 millimolar concentration of isoleucine, we have 14 milligrams per liter of nitrogen. So if we take our 2 millimolar times the 2 millimolar, actually I think I should be a little more exact about this one. I should always be clear about what we're talking about. So 2 millimolar isoleucine times 14 grams of nitrogen per 1 millimolar isoleucine means we've got 28 grams of nitrogen, milligrams of nitrogen in this nitrogen per liter, right? That's the concentration in our cuvette, is 28 milligrams of nitrogen per liter. We don't have a whole 28 milligrams of nitrogen because we only have 50 microliters. Aha, that's microliters. All right, I should probably start this whole thing over. That's microliters, not milliliters. So let's change all of these to microliters. If you wanted me to go slow in this video, I'm actually doing that because I'm making so many mistakes. All right, so those are microliters. So we only have 50 microliters total in our cuvette. So we don't have 28 milligrams of nitrogen, but 28 milligrams of nitrogen is our concentration. 28 milligrams of nitrogen per liter is our concentration. All right, so that's how we get from isoleucine concentration in our standard cuvette to milligrams of nitrogen concentration. So this is how we set up then all 4 of those standard cuvettes again. Here's the top part I just showed you. This part here is the same as it was on the prior slide. And then I elaborate on that here. Here's our standard concentration of isoleucine. I do have the units over here, millimolar. Again, this would be microliters up here. Then I have the dilution fraction, so I have 0.2, 0.6, and 1, just like we talked about in the prior slide. So then I can calculate the isoleucine concentration in the 50 ml sample, all right? And that's in millimolar. So we have 2 millimolar concentration in cuvette 2, 6, and 10 millimolar in 3 and 4. And so if we have 14 milligrams of nitrogen per millimole, this would be should be per millimolar. Oh no, per millimole, that works. Same thing. In this case, we can use the 14 per millimole and multiply it out, and we get our milligrams of nitrogen per liter of sample. So then we have our milligrams of nitrogen per liter, and then what did we do? We just ran the standard curve and we got some absorbance numbers for each of these cuvettes, right? And we had 0 for this one because there's no nitrogen in there. And we had, in one example, 0.258 as the absorbance for this one. We had 0.66 for this one. And we had 1.148 for cuvette number 4. All right, so these were the A335 numbers. Those are the absorbance numbers. So then we just set up our standard curve. So it would look something like this. Here's our A335 up here. Here's our milligrams of nitrogen. We just took those numbers and set up this standard curve. We got the equation for the line, right? So these 4 points would be 28 milligrams, 84 milligrams of nitrogen. This would be milligrams of nitrogen per liter, probably more appropriately. And then this one is 140. All right. And then you can go across and look at the corresponding absorbances that are shown in the table here. If you don't remember how to get the equation of the line, remember you set up the line in Excel, you highlight these points in Excel, you go to add chart element. At the bottom there'll be a trend line, and at the bottom of the trend line, if you click on the options there, you can click options to add an equation and display it on display the equation on the chart, and display the r squared, which gives you how well it fits. This one's very close to 1, meaning our points fit on our linear standard curve very nicely. Okay, so now that we've got the equation and the standard curve, now you have to just get the A335 for your juice. So if your A335 for the juice, say it was, let's say for example, our A335 for the juice, let's just say it was 1.0. We nailed it, 1.0. So then we just set up the equation, right? 1.0, that's our absorbance, so that's our y up here in our equation, right? Because the absorbance is on the y-axis here. So absorbance of 1.0 equals 0.0081 x plus 0.0086, and we would solve for x, so x equals 1 minus 0.0086 divided by 0.0081, and we do the math, and I'm not going to take the time to do the math here, but we're going to get a number if we just read across to our line. There's absorbance of 1, right? So we can go up to our chart. If we read across to our line at 1, we're going to, and we come down from there, and again, if I could draw a straight line, oh, I totally can't draw a straight line with this tablet. Anyway, if we came down there to the x-axis then and read the number, if someone could draw a straight line, then we'd see that the number is going to be somewhat around, let's just say, approximately 130. All right, so it's 130 milligrams of nitrogen per liter. That's going to be our concentration in our juice. Voila, we're in good shape. We got it. All right. So we could, that's basically it. That's basically what you need to know. I think the one other thing to think about is the fact that we are using a 50 microliter sample in every case, in every assay. It might be 10 microliters of 10 millimolar isoleucine plus 40 mils of water to make up the 50. Or it could be 20 microliters of 20 millimolar isoleucine plus 30 to make up the 50. Or it could just be 50 of juice. But since we're always using 50 microliters of sample, we can translate the standard solution directly to wine. We're using 50 microliters of the standard, and we're using 50 microliters of wine. I should really say juice here, because we're testing nitrogen in juice, not in wine. But we're doing 50 in either case, so we don't have to take into account the dilution that happens in the cuvette, because that dilution is the same for the standard solution and the juice. In other words, the concentration of isoleucine in the cuvette is lower than the concentration of the isoleucine in the 50 microliters that we added to the cuvette. Right? Isoleucine, when we add the 50 microliters, it's diluted in the cuvette. But we don't have to worry about that, because all we would do is get a dilution factor there. And then we calculate for the wine, which is diluted the same amount, and then we would, or the juice, and then we would take that dilution factor and multiply our results to get the actual concentration back in the juice rather than the juice in the cuvette. So I hope that makes sense. So we don't have to take into account the dilution. We can go directly from the concentration of isoleucine in the 50 microliters, and we can use that due to our standard curve. And since we have a 50 microliter sample of juice, it's a direct conversion. All right. I hope that all helps. Thanks for watching. Shoot me questions if you've got them, and we'll see you in class.